All right, we're back on the air. First thing is, with respect to homework number 1, I graded those and handed them back. Remember that the people who were taking the course through feeds who were off-site, off-campus, they have a week, officially they have a week longer to do all of the assignments. The people who were in the taking the feed section that pick up their DVDs at the media center are supposed to be on the same schedule as the people who are in class. So homework number 2, there seemed to be some disagreement or misunderstanding as to when it was due. I wasn't sure when it was due, so since I guess I'm the ultimate authority on that, I don't know. I thought it was due today. Some people say it's due in a week, so if you haven't done it, then make it due in a week. So shouldn't be any problem with that. Now, as far as the homeworks go, especially I mentioned this in homework 1, many people just handed in the cover sheet with the answers. In the future, in all of these assignments, they're all in the same structure. So in every case, what I want is the actual simulation code that was run, the actual output that it produced, and if you did any theoretical work, which in the future there will be some, then you should show all your theoretical work, explain it. If you used a program to calculate some things, then show me whatever code that was. Whatever background stuff was necessary, include all of that and make it as clearly written as possible so I can see what you did. And then in the end, copy all of the relevant results in a table and hand that in. So that's just for the future. Now, there also seems to be some question about when you run these simulations, they take a long time, and some people seem to be having problems with running them long enough that the counter doesn't go beyond a certain value, small value. That depends, I guess, on the programming language and the version of it. For example, QBasic is, from a syntax point of view and a logic point of view, is just about the simplest thing there is. But it's slow, and maybe it would be better if you use something like, there's a language called UBasic, which I think is the same as QBasic, but more like Fortran, more sophisticated. Of course, you can use other languages too, so that's up to you. The programming aspect of it is your problem. I don't really know much about programming, so that's why I use BASIC, because it's really simple-minded. And especially since I don't ever actually run any programs, I just write the code, and then, of course, being the optimist that I am, I assume that if you ran that code, it would work. And usually it does. The problem, if it doesn't work, is because of the particular programming language that it's implemented in, but not the logic. But in any event, if you have any questions about programming, everybody in the class can get together and discuss it, and maybe among you can figure out what the best way to do this thing is. But it's all up to you. I don't care about that. From my point of view, the simulation is just there to better understand the theory, but I'm not interested in programming and simulation for its own sake. Okay, are there any questions at this moment? So homework 2, there's a part where I asked you to explain why the answer turns out to be what most people would think is counterintuitive. And of course, an explanation, there's 2 explanations. One explanation is that's what the mathematics predicts, but that's really no explanation. And besides that, I gave you the formulas. I didn't ask you to derive them. That'll come later on in the course. But what I'm really looking for is an intuitive explanation, but that's kind of vague. Different people have different intuition, and maybe this is a hard question. So I want you to think about it. If you can come up with some kind of explanation, that's great. If you can't, well, okay, do the best you can. And then I'll give you an explanation in class after I've collected all of these things, which I hope you will agree, actually does explain what's going on much better than the mathematics does. Mathematics simply turns a crank and gets some answer. But the fact that the mathematics produces this strange result and simulation confirms it means that it's correct and something you should try and understand. So there's no questions at this moment? So the last thing we were talking about was birth and death processes. So let me review what we did there quickly, and then extend it to the next case. So the idea was that we have this system, and the name birth and death reflects the fact that the model, I guess it was originally in people's minds, is there's a biological population, and that population grows and shrinks. So it grows through birth and it shrinks through deaths, and the idea is to model that and calculate the probabilities that the system is in a certain state being the size of the population, as a function of time. And in our application, we're going to look at the births as being arrivals and the deaths as being departures. And so it might look like this. Maybe this is n of t. That stands for the number in the population or the state of the system at time t. And you start out in some state, and then you evolve through births and deaths. And the births and deaths occur at random instants, and this is the thing that you want to model. So we start off with this idea that what we're going to do is we're going to look at this system at time t and time t plus h. And write the probability of being in any state at time t plus h in terms of the probability of being in neighboring states at time t, and then having whatever transition is required to drive the system from this state to that state. And then the trick is to let the h go to 0, and the end result is that you get, if you make the proper assumptions, you get a set of differential equations. And then we solve the differential equations for certain cases. We see that everything works out nicely, and then we try and figure out what's actually going on, what's going on behind this. So let me do it quickly. Actually, quickly is maybe better. I think this time it'll maybe be clearer than it was when I try and include all the details. So I say, what's the probability that at time t plus h, I'm in state j? And I say, well, that's the probability that at time t, I was in state j minus 1 and a birth occurred. Or at time t, I was in state j plus 1 and a death occurred. Or at time t, I was in state j and no change occurred. Or I was in some other state, and the other state then would have to be at least 2 steps away. So one of the things we're going to put in this model is we're going to say, well, the likelihood of having multiple births and deaths in the interval of length h is going to be so small that we can ignore it, especially in the limit as h goes to 0. So in effect, what we're saying is we're allowing only single births and single deaths at a time. Okay, now the theorem of total probability says that if I want to calculate this probability, I calculate these probabilities, or I write these probabilities, and then I multiply each by the conditional probability that if I'm in state j minus 1 at time t, then I will be in state j at time t plus h. So I want to multiply this by the probability that I have a step up of size 1 in the interval of length h. And now here is where I make my important assumptions. The first thing is that this probability is going to depend not on t. It's homogeneous in t. It's going to depend only on the past history through the current state. So whatever is in here is going to have depend on the j minus 1, but it's not going to explicitly depend on the t, although that's implicitly in there because the past history reflects how I got to state j minus 1. The second point is that the probability of making this transition depends only on, or is proportional to, the length of the interval, which in this case is h. So that means that this so-called transition probability is going to be given by lambda sub j minus 1 h plus little o of h. Okay, the lambda sub j minus 1, that's a so-called birth coefficient, and we'll specify the particular lambdas later. And the subscript means that I'm allowing that coefficient to depend on the state of the system at the beginning of the interval. It's the proportionality constant. There's the length of the interval h, and then this is an error term which corresponds to multiple births and deaths that would still get me from state j minus 1 to j. And the little o of h is going to be something that I'm going to assume is so small that I can cancel it out at the end of my analysis. Now, whether or not that makes any sense, other than mathematically, we'll see. The answer is, of course, it does, or I wouldn't be doing this. But I'm trying to be as flexible as I can in my assumptions about what causes the births and deaths at first, and then I'll specialize later. Okay, so here's the first term. Similarly, if I'm in state j plus 1 at time t, then the way I will get to state j would be by having a death. Again, the probability of a death in the interval of length h does not depend on t and is proportional to the length of the interval. And the proportionality constants, or death coefficients, we call mu, and we allow them to depend on the state at the beginning of the interval. So there's a mu sub j plus 1. And then there's the same error term. So I'm just collecting all these error terms and calling them O of h, because I'm going to ignore them later on. The third term, what's the probability now that if I'm in state j at time t, I will still be in state j at time t plus h, which is the probability that in the interval of length h, nothing happens. I have no births and no deaths. So if the probability of a birth in the interval of length h is essentially lambda jh, and the probability of a death is essentially mu jh, then the probability of neither should be 1 minus that. So here I'll put in 1 minus lambda j plus mu j h, and then the little o of h. I don't have to worry about the sign of it, whether it's a plus or a minus. It's just a small amount of garbage that I'm going to get rid of. And then finally, there's the probabilities of transition from all the other states, which are at least 2 steps away. We're saying that for all practical purposes, we don't have to worry about. We don't want to have simultaneous births and deaths, so I'll call that little o of h. Okay, so this is our starting point. These equations represent the theorem of total probability adapted to the particular case in which the conditional probabilities are given by these terms. And in that case, this is called the birth and death process. Okay, so now we want to get something out of this. And so I think what I'll do is I'll move up here. So what I'm going to do is, first of all, I'm going to multiply this pj times 1 and move that over to the left-hand side. So that's going to give me p sub j of t plus h minus p sub j of t. Okay, so that takes care of this guy. And then I'm going to multiply all of these terms out. And when I do, this term over here has an h multiplying it, and then there's an O of h times the p. But the p is a number between 0 and 1. It's a probability, certainly not infinite. So if I multiply this by this little garbage, I'm still going to get only little garbage. So multiplying the O of h by any finite quantity still gives me something that's called O of h. So that means that when I multiply this out, what I'm going to get is the following. I'm going to get lambda sub j minus 1 times h times p sub j minus 1 of t. And that h, which multiplies all of the terms, I'm going to divide both sides of the equation by that. So that's going to put the h over here and get rid of it over there. Okay, similarly for this term. So the coefficient is now mu sub j plus 1. Here's my p sub j plus 1 of t. The h has been divided out, so it's right there. And the O of h is going to be collected at the end. The next term is minus. That's this guy right here. Let's see, this looks like it's running out of ink. Okay, minus lambda j plus mu j. The h has been divided out. and then I have the pj, and then I have all the O of h's combined, and so they are O of h. Except that I've already divided out by h, so I have to divide those terms by h, so I get that. Now I let h go to 0. So I'll erase this guy here. It would be better if this were a real classroom and I didn't have to erase things in order to get room to write, but what are you going to do? All right, so now I'm going to let h go to 0, and this is the key. So you see over here, you recognize this as being the definition of the derivative. So this is the derivative with respect to t of pj of t. Of course, that assumes that h goes to 0 through positive values. It has to be the same if it goes through negative values. But we're not worried about the mathematical details of analysis here. So I'm doing the engineer's argument. Not that the engineer is not as smart as a mathematician, but the engineer, or the physicist maybe I should say, is thinking in physical terms and worries about justifying the details later. If you're worried about justifying the details as you go along, then you get bogged down in mathematics, maybe never get done. And from our point of view, that's not the point. Okay, so we're going to let h go to 0. We're going to call that the derivative. Now on the right-hand side, you see that we don't have any h's here, but we have this h right there. Okay, now this is the key, which is that when h goes to 0, I'm going to assume that this thing goes to 0. In other words, the ratio of all of these little errors divided by the length of the interval goes to 0, which means that the numerator goes to 0 faster than the denominator does. So whether or not this makes any sense, what this actually means, we don't know, although you're going to see shortly that it essentially implies that the functions we're talking about are exponentially distributed. But right now, I'm just making that assumption because that's what I have to assume in order to make this thing work. So that gives us this derivative is equal to lambda sub j minus 1 p sub j minus 1 of t plus mu sub j plus 1 p sub j plus 1 of t minus lambda j plus mu j pj of t. And these are equations 2.3 in the textbook. So now I have a set of potentially an infinite number of simultaneous differential equations. But they're sort of simple in one sense because, first of all, they're first order, meaning that the derivative appears only as a first derivative. And they're linear in that there's no nonlinear terms. The functions aren't squared. There's no t in the coefficients. So these are linear first-order differential equations with constant coefficients. So that makes them simple. The difficulty is that they're simultaneous equations because I have to know what the stuff is that fits in here in order to be able to solve these equations. Okay, so this is, once you see it from this point of view, I think it's sort of clear what's going on. Now, whether or not it makes any sense, well, that remains to be seen. Notice that I didn't really assume very much about what the functions p were. I reasoned with them as probabilities because I'm using the theorem of total probability. But other than that, I haven't stated explicitly any restriction that says that they must be lie between 0 and 1, for example, or that they must sum to 1 if I add them up for any fixed t over all values of j. So if that happens, then you should say, wow, that means that we must have done something right. Okay. So now what I wanted to do, what I did was I looked at this for particular cases. So case number 1 was the case which is called the pure birth process. Pure birth process. And based on its name, what it says is that we're going to look at the process in which we'll assume that the population never gets smaller, which is equivalent to saying that I'm going to count the number of births or count the number of arrivals. And a good example of this might be a Geiger counter, let's say, where every once in a while you get a click and the number of clicks, cumulative number of clicks, jumps up by 1, and you want to see what the probability is that after time t, the number of clicks that have been counted is is any particular value, all particular values. So by pure birth process, that means that in these equations, I'm going to plug in all the mu's equal to 0. But also, I have to decide what the lambdas are. So I'm going to also assume that the lambdas are constant. Simplest possible assumption. Okay, what that means is that the probability of a birth in the interval of length h would be lambda h plus this little garbage stuff. So in other words, it's proportional to the length of the interval, but it does not depend on how large the population is. So if you were modeling a biological population, that's probably not too realistic, because the larger the population, the more members there are who are eligible to give birth. But if you're doing something like counting the number of amount of radioactive decay, let's say the number of clicks in a Geiger counter, or you're counting the number of messages that have arrived to a channel for transmission in the internet, it's reasonable to assume that the probability of that occurring in a little interval of length h doesn't depend on how many messages have arrived in the past or how large the population is, how many Geiger counter clicks there have been. So this says that the birth coefficient is constant. So now what we do is we substitute these values for the lambdas and the mu's in here, and that simplifies things. Because first of all, these terms with the mu's cancel out because they're 0 multiplied by 0, and the terms with the lambdas, well, they're simple because the lambdas do not depend on j, they're a constant. So you can write those equations, and you need an initial condition. And the initial condition I'm going to assume here is that at time 0, the number of births so far have been 0. In other words, I'm going to start counting at 0. So that means that I'm going to assume that the probability that at time 0 I'm in state 0 is 1. And since the probabilities for any particular time must add up to 1, that means the probability of being in any other state must be 0. So that's the same thing as saying that I start out in state 0. So in other words, I'm going to get a picture that looks like this. I'm in state 0, then I get a birth, then another birth, then another birth, and so forth. And so the thing just keeps on rising like that. And what I want to know is, what's the probability that at time t, I'm exactly at level j? Well, it turns out that when you solve these equations, the solution turns out to be the following. Pj of t is equal to lambda t to the j over j factorial e to the minus lambda t for every value of j. So you get this really nice simple formula. And you recognize that this formula represents the Poisson distribution. That is, by definition, if the probability of being in state j, it's a discrete distribution now because t is fixed, the probability of being in state j is given by something to the j over j factorial times e to the minus lambda, whatever that something is, then by definition, that is the Poisson distribution. So this is standard stuff that you learn in an undergraduate course. And you see, first of all, well, everything sums to 1. For every t, there's a different numerical values because it depends on t. But for every t, this thing sums to 1. And you never have any negative values. This is a probability distribution. So that comes right out of the equations. Also, you know that that the expected value of this distribution, remember n of t is the random variable here, number of in the population at time t. If you take the expected value of this Poisson distribution, you get lambda t. And since t is the length of the interval under consideration, and lambda t is the average number of arrivals, then lambda must be the arrival rate. So the parameter that appears right here is in fact the arrival rate. Now, if this describes the number of arrivals in a fixed time for every possible fixed time, that means we can show, it's easy in fact, that the times between arrivals must be exponentially distributed, independent, identical, exponential. So in other words, this these equations for these particular assumptions, the pure birth process defines a Poisson process. So this is a Poisson process. So the fact that we were able to describe this process, be able to generate this result, this Poisson process, by means of these relatively straightforward, simple assumptions, means that obviously we're onto something here. Okay, so the pure birth process with constant birth coefficients gives a Poisson process. Then we looked at the pure, so-called pure death process. Now the fact that, to step back again, the fact that these are differential equations, from our point of view, this is not going to be important. All you have to recognize here is that a differential equation is an equation that relates some functions to the derivatives of those functions. And the idea is to find the function that satisfies the equation. And once you have the solution, a solution, you can simply substitute the solution back into the original equation and show that it is a solution, that it works. That is, the left-hand side equals the right-hand side. So although there may be lots of tricks, it may be difficult in general to find a solution to a differential equation, once you have a solution, it's easy to verify that it is in fact a solution. And then you want to worry about some other questions like, well, how do I know that solutions are going to exist? What about uniqueness? Well, we don't have to worry about existence, because if we found it, obviously it exists. As far as uniqueness goes, in most cases, it's from our point of view, for the things we're going to be considering, it's intuitively obvious. So we don't have to concern ourselves with the mathematical details of proving existence and uniqueness. Okay, now in a pure death process, what we say is now we don't allow any births. So the lambdas are all 0. And again, just like over here, I'm going to make an assumption about the way the deaths occur. So I'm going to assume now that the death coefficients are proportional to the population size. So let's call that J mu. So the mu is a parameter, which we don't know what that means at the moment, but it'll come out of this, just like the lambda. But now I'm making things a little bit more complicated by saying that this coefficient depends on how large the population is. From a viewpoint of modeling a biological population, that makes sense, because what you're saying is that the more members there are in the population, the more likely you are to have a birth occur. And this says that that coefficient is going to be proportional to the population size. In our applications, the deaths will correspond to service completions, which means that this is going to be the deaths are going to correspond to customers completing service. And if the customers are being served in parallel, then the death coefficient should depend on linearly on the number of customers that are being served. In fact, we already assumed that when we looked at the Erlang B and the Erlang C, so this is going to be the same idea. Okay, now here, since we have only deaths, if we were to draw the diagram, we're going to start out in some state, which I'll call little n, and then the deaths are going to occur at random. One difference between this death process and the birth process is the birth process goes on to infinity, so the population size keeps on getting larger. In the death process, when you get to 0, you stop. Okay, so now we plug these values into the equations 2.3, just like before when we solved them. And now we have an initial condition which says that the probability that at time 0 I'm in state n is 1. and therefore the probability of being in all the other states is 0. Yes, a question? Yeah, the question is, explain this again, this piece right here. What I'm saying here is that if you're talking about a biological population, the larger the population is at the beginning of the interval, the more likely you are to have a death. The more people we had in this class, the more likely we are to have a death before the lecture ends, right? So hopefully it's small enough so that this probability is pretty tiny. In terms of queuing theory, if the deaths represent service completions, then the more customers there are in service, the more likely you are to have a customer complete a service. And this just says that we're going to make that likelihood, we're going to model that by saying that the death coefficient is proportional to the population size. Okay, so now we have to solve the equations. They're more complicated than the equations for the pure birth process because these coefficients depend on the state, but there's a simplification in the sense that there's only a finite number of these, whereas in the case of the pure birth process, there's an infinite number. In any event, when you write down these equations for this case, it looks more complicated, but the important point is that we can solve it. And so here is the solution. The solution is given by this. Pj of t equals. It's the binomial coefficient n choose j, e to the minus mu t to the j, 1 minus e to the minus mu t to the n minus j, for j being 0, 1, up to n. So this is maybe looks more complicated than this, but not really. Now, everybody should recognize that this is, in fact, the binomial distribution. So once again, even though I didn't seem to explicitly assume very much, what comes out of here is a probability distribution. So these numbers are all lie between 0 and 1, and for any t, they sum to 1. And in fact, you could say more than that, because now you can give another interpretation. Suppose I had asked this question. Suppose I said that each member of the population lives and dies independently of each other member of the population, and the expected value of the lifetime of a member of the population, let me put it this way. Each member of the population dies independently of each other member of the population, and the lifetime of each member of the population is exponentially distributed with parameter mu, which would mean that the average lifetime of each member of this population would be 1 over mu. If I stated the problem that way and said, okay, I've got n independent members of the population, and each one of them has an exponentially distributed lifetime, what's the probability that at time t, exactly j of them are still alive? And I'd say, well, if they have exponential lifetimes, then 1 minus e to the minus mu t is the probability that an individual member of the population lasts less or dies before time t. And e to the minus mu t is the probability that he lasts longer than t. So the probability that exactly j of them would last longer than t would be the probability of any one of them lasting longer than t to the j times the probability of any one of them lasting less than t to the n minus j, multiplied by the number of different ways I can pick the j individuals out of the n, which is the binomial coefficient. So even though I didn't assume that the members of the population behaved independently of each other, because this equation expresses what happens in the aggregate, the result is just as if they did. So we could see that this, in fact, is going to reflect the idea that the birth and death equations are going to describe Poisson, among other things, systems with Poisson arrivals and exponentially distributed service times. So that's coming out of this. We're not done yet because we've only looked at births and deaths separately, but that's what we've gotten here. Okay, so this is what I did last time, and now we want to look at the birth and death process. So now, in one model, the same model, I'm going to allow both births and deaths. The reason that we were able to solve the equations easily for the pure birth process is that once we set all the mu's equal to 0, we could solve the equations by successive substitution. So you could solve them one at a time. You didn't have to solve them simultaneously. Similarly, in the case in which all of the lambdas are 0, we also were able to solve the equations by successive substitution. So that allowed us easily to get the answer. But in general, you can't do that, because if you go back and look at these equations here, if you were to write them out, you would see that in general there's no way to simply find P1 in terms of P0 and then P2 in terms of P1 and so forth. So it's a difference between solving equations that are simple in that you solve them successively or have to solve them simultaneously. So in general, you have to solve them simultaneously. So the birth and death process is difficult to give a complete solution for in any case, although as I mentioned, if I remember right, there's a famous paper that was written in the 50s that discussed the existence and uniqueness of solutions to these equations. And one of the interesting things about it was that one of the authors was Wolfowitz, who's the father of the Paul Wolfowitz, who was the National Security Advisor to George W. Bush, and I think now is a president of the World Bank or something like that. So anyhow, that shows that queuing theory reaches its tentacles and indirectly affects your lives more than you might expect. Okay, so the birth and death process in general is too complicated to get an explicit solution for, but there is one case that's easy and that's worth looking at, and that's the case of what's called an alternating renewal process. So let's say, for the sake of example, we start out in state 0 and then we have a birth, and we go to state 1. And in this case, we're not going to allow a step up from state 1. So this is going to be like a queuing system, an Erlang law system, for example, in which you have only one server. So I can be in state 0 or state 1. When I'm in state 1, then I must go back down eventually to state 0. And when I'm in state 0, I later go up to state 1 and so forth. So this is the particular birth and death process I want to solve. So that means that what I'm going to do is I'm going to assume that lambda sub 0, which is the coefficient that corresponds to a birth, a step up when I'm in state 0, I'll call that lambda. And mu sub 1, which corresponds to the coefficient that describes a death when I'm in state 1, I'll call that mu. And all the other lambdas and mu's are 0. So when I'm in state 1, I'm not going to allow a birth. And when I'm in state 0, of course, I never allow a death. I can never go to a negative state. So I have the birth and death process, which has both lambdas and mu's, but there are now only going to be two states, because there's only going to be state 0 and state 1. So I think I'll do that over here. So now I'm going to specialize these equations. I'm specializing these equations to this case, the birth and death process. So that means that I'm going to have an equation like this for P0. So when j is equal to 0, this term is 0 because that corresponds to an impossible state. This is going to be mu sub 1, which is simply mu according to our assumption, P1 of t. This is going to be lambda 0, which is a lambda times P0 of t. And this is going to be 0 because we don't allow death when I'm in state 0. So this relates P0 and its derivative to P1. Similarly, I'm going to have an equation for P1 of t. Derivative with respect to t. Now, when j is equal to 1, this would be lambda sub 0, which is lambda P0 of t. This term would be, let's see, j is 1, so this would be mu 2. This would be P2. This would be an unallowed state, so its probability is 0. This would be minus lambda sub 1, but lambda sub 1 is 0 because we don't allow bursts when I'm in state 1. And this would be mu sub 1, which is mu. Okay, so when I write these equations for the particular birth and death process we have, we get these two equations which must be solved simultaneously. But it turns out that in this particular case, life is easy. Because for one thing, I can add them up. And then I see that the derivative with respect to t, now, remember that this is a linear operator, so that plus that is the same thing as the derivative of P0 of t plus P1 of t. When I add up the right-hand side, I see that that term cancels with that term cancels with that, and so I get 0. But that tells me, that implies that P0 of t plus P1 of t must equal a constant. And if I require initially that the system be described by a probability distribution, then if it's ever described by a probability distribution, it must always be described by a probability distribution. So in other words, to say that P0 of 0 plus P1 of 0 adds up to 1 implies that this constant is 1. So that means that a conclusion that we get from these equations is that P0 of t plus P1 of t must equal 1. So already that's good news. Things seem to be working out. Okay, now I'm going to use this fact, which I can't get away with in general, but I can in this case where there's only two equations, because I could say, all right, well, now is I'll assume, use this, and that implies that P1 of t must equal 1 minus P0 of t. And likewise, P0 of t equals 1 minus P1 of t. So this means I can go back to this equation, for example, and I can replace P1 by 1 minus P0. Okay, so the P1 that fits right here is 1 minus P0. That means that this equation then contains only P0, which makes it a linear, ordinary, first-order differential equation with constant coefficients, the kind that any person taking a first course in differential equations, a junior level student, could solve. So it's standard, straightforward stuff. So let me write down what the solution is. And this is given, by the way, in the textbook. This is equation 218 that I'm writing now. Okay, so I'll do this here. And what I'm doing is I'm writing the solution for the birth and death process for those lambdas and mu's. So what I get, according to 218, is that P0 of t is given by, according to 218, mu over lambda plus mu plus P0 of 0 minus mu over lambda plus mu times e to the minus lambda plus mu t. If I copied, 218 right. And 219 gives the corresponding result for P1 of t. And of course, P1 of t and P0 of t are just reflections of each other, with one having lambda replaced by mu and vice versa. So I can write down again the answer immediately. It's going to be lambda over lambda plus mu plus P1 of 0 minus lambda over lambda plus mu e to the minus lambda plus mu t. So that's my solution. Now I could draw the graph of that. For example, here is, let's say, here's P1 of t. Here's t. And let's suppose that at time 0, I'm in state 0. For the sake of argument, that's what I have here. So that means that P1 of 0 would be 0. So I plug that into here, and I plot the graph, and I see that I would get something that would look like this. And likewise, I could plot P0 of t, and it would be something that would look like that. Okay, so let's say here's the value 1. And you can see that this curve for P1 of t is going to be asymptotic to this value right over here. Because as t goes to infinity, this term goes to 0, the initial condition goes away, and I'm left with lambda over lambda plus mu. So this is lambda over, let's see if we got, okay, let's see, where was I here? Lambda over lambda plus mu. Now, it's worth looking at this, examining this, and to see what goes on. Let me erase this thing right here. So I want to make some observations about this. But let me just step back for a moment. What did I do? We started with these equations. We specialized to the particular case in which we just allowed the system to go back and forth between state 0 and state 1. We solved the equations, and we got the explicit formula for the probabilities of being in each of the states at time t. Okay. Then we noticed that if I looked at any one of these things, that if I drew the curve, it represents a curve that starts out at either 0 or 1, depending on what the initial condition is, and then it is asymptotic to whatever this final value is, which is right here. That would be the limiting value. All right, so I'm now kind of merging into section 2.3, which is called Statistical Equilibrium. So this is 2.3, Statistical Equilibrium. The idea is that, well, first of all, in reality, if I'm solving this for any practical reason, do I really want to know the probabilities at specific points in time? Do I care what the probabilities are after the system has been in operation for exactly so many minutes or something of that sort? Probably not. What you're usually concerned with is you say, well, I got this system, and it's in operation, and there were some initial conditions, and eventually those initial conditions should wear off, and then I should be in some kind of equilibrium. That is, what I want to know is if I look at the system at some time which is far enough removed from when I looked initially, what are the probabilities that describe where I'm going to find the system? So that corresponds to the limit as t goes to infinity of the probability of being in state t. Let's say state 1 for our particular case. Okay, so what's the probability that after a long enough time I'm in state 1? Okay, well now if you look at this thing, you can see that if I take this limit, that this term here, which has the initial condition goes away. So the answer is independent of the initial condition, and in fact it's given by lambda over lambda plus mu. Similarly, the limit as t goes to infinity of p0 of t from this equation is equal to mu over lambda plus mu. And that plus that, those things there, add up to 1. So this thing then has a limiting value which I'll call p1. That has a limiting value which I call p0. And the limiting value is independent of the initial condition, as you could see by simply taking the limits in here and here. So obviously the limiting values are the probabilities primarily of interest. And it'll turn out later that when we actually want to make these calculations, what we want to calculate is the limiting probabilities. So how do we get the limiting probabilities? Well, we got them by solving the equations and then taking the limits. But let's look at a couple of other properties of this and then see how we're going to calculate this, because in general the equations 2.3 are too difficult to solve and then take limiting probabilities. So what I'm going to suggest here, what this is going to suggest, is that there's a trick, there's a way around this, which is not to get a complete solution and then take the limit, but to assume that the limit exists and then find it directly, and of course that'll turn out to be exactly those values right there. All right, so one of the things is, let's look at this limiting value. Here we have the solution for in terms of the initial condition. Now, suppose that the system is in statistical equilibrium. In other words, suppose it's been in operation long enough, or for some reason, that if I'm going to look at it, the probability that I will find it in state 1 is lambda over lambda plus mu. And the probability that I will find it in state 0 is mu over lambda plus mu. Okay, now, if the system, for example, suppose at time 0, this probability, the probability of being in state 1, is given by its equilibrium value, then you can see that that is the same as that. That is the equilibrium value. So therefore, this cancels out, and so the dependency on time cancels out, and my probability is still given by the same answer, which is the limiting value. Now, in other words, what that says is that if the system is ever in equilibrium, if it is ever described by its limiting values, then it'll always be described by its limiting values. Because if I take as my initial condition, whenever I'm going to look at it, if that probability is the limiting value, then the probability for all time measured from that point on is the same limiting value. Now that property is called stationarity. In other words, this is said to be a stationary solution, which means that, in an intuitive sense, that once you reach equilibrium, you stay in equilibrium. But this is very tricky, because the state of these systems depends on two things. One is it depends on the configuration of the system. That's what these equations represent. It also depends on your state of knowledge of the system. That's what the initial conditions represent. So if I have a system that is described by its equilibrium distribution, then if I don't look at it, it will always be described by its equilibrium distribution. But if, okay, here it is, here's my system, and it's oscillating between these two states at random. Now, if I look at the system, then when I observe it either in state 0 or state 1. So that means that from that point on, I now have a new initial condition. So that as soon as I look at the system, the equilibrium distribution is destroyed. But if I wait long enough, the equilibrium distribution comes back. Of course, how long you have to wait from a practical point of view, that's another question. But the point I'm trying to emphasize is that the equilibrium probabilities are such that when you are in equilibrium, you stay in equilibrium, which means that the probabilities will always be defined by the same formulas. But as soon as you look at the system, then you have a new initial condition, and in effect the system starts over again, and now you have this solution again, which will again approach the equilibrium solution, but the act of observing changes the amount of information, so therefore it changes the probabilities. So the probabilities that describe the system depend on the physical configuration of the system and your knowledge of the system. It's always true with probability, but this is a very tricky concept. The probability of something is a mixture of the physics of the thing whose probability you're calculating and what you know about it. Right? If I toss a coin, I could say that before I flip the coin, the probability of head or tail is 1/2. That's based on my feeling about the way coins work. Once the coin lands on the floor, it's not 1/2 anymore unless I haven't looked. If it's landed on the floor and I've stepped on it but I haven't looked at it, then the probability that a head is facing up is still 1/2. But if I have looked, it's not 1/2 anymore. Once I pull my foot away and look at the coin, then I either see a head or a tail, and the probability is now not 1/2. It's 0 or 1 depending on what I saw. So there's a mixture here in that probability defines or describes the thing the coin that you're tossing. It also describes your knowledge of the coin that you're tossing. So the same kind of thing is true here, but this is a more sophisticated kind of example. Okay, so the probabilities are stationary. So the statistical equilibrium distribution is the stationary distribution. Now, the distribution is also said to be ergodic. So what we're talking about here, these are concepts from the theory of stochastic processes. And so to understand these things in depth, well, one argument is you could study more and eventually get there. Another argument is that no matter how much you study, you will never get there. Even more depressing argument is that the more you study, the farther away you will be, because the more you'll realize you have no idea what's going on. But I can at least explain what ergodic means from an intuitive point of view. And so here's the notion of ergodic. So let me draw a diagram here. So if you go to books on stochastic processes and look up things like stationarity and ergodicity, you'll find all kinds of stuff. And in fact, if you're knowledgeable about physics, you know that there's the word ergodic, for example, appears in statistical physics all over the place, and probably lots of other places. I don't know. These words tend to have various specific meanings for different subjects. Okay, so the question is, we have this system, and what it does is it oscillates from state to state. The length of time it spends in each state is random, and we know the probability that it stays that describes that it's in a particular state. But then I could say, well, how do you interpret that probability? What does that probability mean? And one argument goes, well, probabilities are frequencies. So that means that if I sample this system at random, that is, I just kind of closed my eyes, walked up to the board and drew a line, the probability that I would intercept a state, the state 1, would be given by whatever the formula is for P1. And the probability I would be given find state 0 would be whatever the formula is for state 0. But if that's true, that means that the fraction of time that I'm in each state must be the same as the probability that if I sampled at random, I would find that state. So one interpretation is, if I wanted to find, for example, P1 from simulation data, then what I would do is I would generate this diagram, and I would measure the total time that I'm in state 1, divide that by the total time. The fraction of time I'm in state 1 would be P1. Okay, so P1, which is lambda over lambda plus mu, that's the fraction of time that the system spends in state 1. But there's another way I could look at it. Because, after all, if you think about it, if you're looking from a queuing theory point of view, are you simply looking at a single system over all time? Or are you looking at the system as being representative of an ensemble or a class of systems? So let's imagine that we have a whole bunch of systems. So here's system number 1. Here's system number 2. Now, system number 2 is also an equilibrium, so therefore it's an infinite distance in theory away from its last initial condition. So you're going to see a picture that looks about the same but is not correlated with it, like that. So these two systems are statistically or stochastically identical, but they represent different realizations of the same process. Yeah. Okay.
I'm really confused here now. You say that the active observation resets the system and breaks the equilibrium. So how can you ever know if the system's in equilibrium? Because the active observing it breaks that equilibrium.
Right. It's like, well, it's like in, I guess maybe this is being pretentious, but like in quantum mechanics, as soon as you look at the state of an elementary particle, then the wave function collapses or something like that, and it's either here or here. Of course, this is not as sophisticated as that. But yeah, there's a problem here, because you've got this system, and it's jumping from state to state. By the way, I forgot to repeat your question. Okay. His question was, I'm really confused. And then it added a little question onto that, like, what are you talking about? Okay, so this system is jumping from state to state, and we know the fraction of time that it spends in each state. Or in other words, we also know that if we viewed that at random, the probability that we would find it in state 1 would be given by this thing here. But if we look at the same system again, then if we know it's in state 1, for example, when we look, then its future evolution would be described by the same equations, except that we would now have the initial condition, because we're now measuring time from when we first looked. And that initial condition, if we looked, it's either in state 0 or state 1. So if we knew it was in state 1, it would take, in principle, an infinite length of time before the system was again described by the equilibrium distribution. Of course, it may actually happen very quickly from a practical point of view, but the act of observing introduces some bias. But that's not the only way to interpret these things, because in queuing theory applications, you're usually not concerned with what happens, or maybe you don't look at it this way, with what happens to a single system as it evolves. What you imagine is that this system, in a sense, represents a typical system. It comes from there's an ensemble of systems. Those systems are all statistically identical. So in other words, they're like different realizations of the same random variable. So if I take that point of view, so here's system 1, here's system 2, here's system 3, and so on, system 4, system 5. Okay, so in the first interpretation, this represents the fraction of time that a single system spends in state 1, which would be the same for every system. Another point of view is that what I'm going to do is I'm going to imagine that I simply pick a time, and instead of imagining that that time is a random time for a single system and represents then finding it in state 1 should be equivalent to the fraction of time I'm in state 1. Now I'm going to say that, well, I've got an infinite number of systems, and they're all statistically identical. So if I look along this line and I count how many or what the ratio is, what's the fraction of these systems that are in state 1, it should be the same thing. So now I'm going to say that I'm going to calculate this probability by starting here and simply looking at these systems. And if when I look at that time, the system is in state 1, I count it. Since this is in state 0, I don't count it, and so forth. And I imagine that I take this ratio over an infinite number of systems, and I count the fraction of systems that are in state 1. And that fraction should be the same as this probability right here. And you can see that sort of intuitively as long as you recognize that these systems are all statistically identical and they're not correlated with each other. So when I take a view along here, that's sort of the same thing as viewing a single system. Instead of viewing an infinite number of systems at one point, I'm going to view a single system an infinite number of times, but separated by infinite looks. So the equality of those 2 points of view, that is, one system where the probabilities represent the fraction of time, the other viewpoint being an ensemble of systems, and the probabilities representing the fraction of systems, the equality of those 2 points of view is said to express the fact that the systems are ergodic. Now, if you're studying stochastic processes and you want to know under what conditions are systems ergodic, or what does ergodic really mean, I don't know. That's not my bag. From a queuing theory point of view, I keep in mind this picture. And when I want to, I interpret the probabilities as representing a single system. And if I want to, I consider the probabilities as representing a frequency of an ensemble of systems. And that seems to work. Gives me the right answers. It's just like in this analogy, not exactly the same thing. If you look at homework 1, where you wanted to calculate the probability of loss, we calculated it 2 ways. One is you calculated the fraction of time that the system was in the blocking state. That's looking at a single system, and you look at it over a long period of time, and you calculate ratios of time. The other was you calculated the fraction of arriving customers who found the system in the blocking state. That was a ratio of integers. It turned out that if the input process was a Poisson process, those 2 numbers turn out to be the same. In principle, they're the same. In simulation, of course, they're going to be slightly different. But in principle, they would be the same if the simulation were 100% accurate. That's called POFTA in the queuing theory formulation. So it's not exactly the same thing, but it's analogous. 2 different points of view. One is a frequency of what is observed by customers when they arrive. The other is the fraction of time a typical system spends in the state. They turn out to be the same in queuing if you have Poisson input. Yeah. His question is, okay. Okay.
We know from what you said, if we observe a single system at point of time t, at any point of time h unit time later, it is described by the equation, by the large equation that we've got there.
No, wait. The h, are you getting confused now? The h was a small interval of time, and that was used in the derivation of the differential equations. And the whole point there was to represent the state of the system, its probabilities, at 2 times that are close to each other, and then let them coalesce so that you could get a differential equation.
Right.
Okay.
I'm just using h as a variable.
Okay. Well, yeah, but I'm using h. I try and restrict h to a little tiny interval. Okay. So, but okay.
At any point in time, you observe the system.
Right.
Some other point in time later, you can determine the probability that the system is going to be in state 1 or 0 using those equations up there.
Right.
Given what you just said about ergodics, could you apply that to looking at a single system, observing the state in that system, and then depending on how many systems you have, apply that as a version of t to figure out the probability of the fraction of the systems being in the same state?
I don't know. I'm not sure exactly what you mean. So so you're as confusing as I am. All I know is that I have this picture in my mind of 2 different diagrams. One looks at a single system evolving over all time and calculates fraction of time you spend in each state. The other looks at multiple systems that are statistically identical but are not synchronized with each other. And then looking at those systems at any one specific time and asking for the fraction of them that are in a particular state. And if the system is ergodic, then the 2 points of view yield the same probabilities. Now, how do you know whether something is ergodic or not? I don't know. All I know is that it's obvious to me that these kinds of systems are ergodic, And since this is not a math course, actually I keep on changing my position on that, whether it's a math course or not, depending on what the question is that the audience asks. So if I have mathematicians in the audience and I get stuck, I claim I'm talking to engineers. And if I got engineers in the audience and I ask a question, I get stuck, I claim I'm a mathematician. So I use this to my advantage. But in any event, what I know here is that in queuing systems, that it seems to me intuitively obvious that these two viewpoints should be the same. And systems for which that's true are said to be ergodic. And this is the thinking that I use when I analyze these systems. Because when I write down equations to describe what's going on, I go back and forth between whatever viewpoint is necessary in order to write the equations. Okay, so where we are now is that I have some understanding of the notion that these equations produce results that are stationary and ergodic. And now the question is, how do I get these results, or in particular, how do I get the statistical equilibrium results for the general case? Because the only thing that I have any hope of solving that's a birth and death process is something that has only one or two states. But if I have multiple states, then it becomes too complicated. Okay. So the answer is, well, look at this diagram right here, and you could see, in fact, you could show from mathematics that that as t goes to infinity, the derivative goes to 0. Right? If the function is going to approach a limit, and that's the only reasonable thing to assume, then and it certainly shouldn't approach the limit by oscillating. Mathematically, maybe that's possible, but from a physical point of view, why should probabilities oscillate? So if the probability is going to be asymptotic to a constant, approach some kind of limit without oscillating, that means that in the limit, the derivative, which is the slope, must go to 0. And if the derivative goes to 0, then I can go back to the original equations, which of course I erased, and I can take the limit in the equations before I solve them by setting the derivative equal to 0 and the probabilities equal to the equilibrium result. So let me write that down, and then I'll start there next time. Okay, so here are our basic equations, if I remember them right, 2.3. Derivative with respect to t of pj of t is equal to, let's see, it was lambda j minus 1, pj minus 1 of t, plus mu j plus 1, p j plus 1 of t, minus lambda j plus mu j pj of t. Equations 2.3. Okay, now I'm going to say that, well, it makes physical sense to say that the limit as t goes to infinity of pj of t is pj, does not depend on t, exists, and is independent of the initial conditions. We observe that for the case of the two-state system, but it's not unreasonable to think it would be true in any case. And the second thing is that the limit as t goes to infinity of the derivative of pj of t would be 0. And we observed that in the case for which you could actually make the calculation. So it's reasonable to assume it'll always be true. Because if you have a limiting distribution, that means the probabilities approach a constant, so therefore their derivative should approach 0. Okay, now if that's true, what I'm going to do is I'm going to take my limit here rather than solving the equations first and then taking the limit. If I take the limit, what I get is 0 equals lambda j minus 1 pj minus 1 plus mu j plus 1 pj plus 1 minus lambda j plus mu j pj. Now, these equations, these are linear equations. There's no time, no derivatives, no differential equation, no nothing. These are just difference equations for the probabilities. And we can solve those equations. That's what I'll do next. We'll get a general solution for these, and then we'll see that the solution here corresponds to rate up equals rate down, which is where we started the course. So it'll turn out then that general rate up equals rate down will be a consequence of whatever was required for the birth and death process. So that should give us a lot more insight into when we can write rate up equals rate down. It really depends on this O of H stuff. So then we'll go back and show that this O of H stuff is implied by the assumption that the underlying births and deaths are caused by exponential distributions, and then everything will be full circle, and then we can go back and start looking at the particular consequences for queuing models. Okay, so this is where I'm going to start next time. Okay.
What I was trying to say earlier is that for a single system, like you said, looking at a single system over an infinite amount of time, given any one observation point on that at that time, any amount of time later,